Hey guys, welcome to video 37. Today we're going to talk about Class B and AB biased amplifiers and the basics of power amplifier operation. So buckle up your seatbelts and hang on because here we go. Alright, a little bit of review to start with. In the last video we talked about Class A amplifiers, and one of the main characteristics of a Class A biased transistor is that its Q point is located around the center of the load line. What this means is when we apply a signal to a Class A amplifier, the Q point moves continuously for the entire 360 degrees of the applied signal. One of the good things about Class A amplifiers is that when they're designed well, they can be extremely linear. One of the bad things is that they're very inefficient, and that's where Class B and Class AB amplifiers come in, because they're much more efficient than Class A and much better suited for power amplifier applications. All right, the main idea behind Class B biasing is that the Q point of the transistor is located at cutoff. This basically means that the transistor is not biased up at all. So if we look at this circuit over here on the right, with no signal applied because there is nothing connected to the base, the transistor is in cutoff. ICQ equals 0, VCEQ equals the maximum VCC, and PDQ, the power dissipation at the Q point, is 0. Now that's a good thing, because when we're not applying a signal, the transistor is not dissipating any power, and that contributes to the greater efficiency of this circuit. But it does have some problems. All right, let's take a look at what happens when Vin goes positive. All right, initially nothing happens because we have to overcome the base emitter barrier potential for Q1. Once we exceed the barrier potential, the transistor starts to turn on and we get an output voltage. All right, the output voltage will be a replica of the input, except it's going to be about 0.7 volts lower in amplitude because of the barrier potential. When Vin goes negative, we reverse bias the base emitter junction and simply drive the transistor harder into cutoff. All right, so we can kind of summarize all the characteristics of this circuit over here. Number one, the transistor is biased at cutoff. The maximum efficiency for this circuit is 78%. We're always going to run at something less than that. The conduction angle of the transistor is less than 180 degrees because we have to overcome the barrier potential before we get anything out of this amplifier. It's got poor linearity. It is used in power amplifiers, and if you want a practical circuit, you have to add a complementary PNP transistor to get this circuit to be functional. All right, usually it's going to be an emitter follower, as we have shown here, and PDQ equals 0. All right, now let's fix this circuit and make it a little bit more practical. So what we've got here is a complementary symmetry push-pull amplifier. We've added the complementary PNP transistor. It's basically identical to Q1, except its polarities are reversed. All right, so it's called push-pull because on positive inputs, Q1 is working and it allows current to flow down through the load resistor from top to bottom. When the signal goes negative, Q2 is on and Q1 is off, allowing current to flow back the other direction to ground through Q2. Now, in this circuit, C2 serves two purposes. Number one, it couples the signal from the amplifier to the load, and purpose number two is it returns energy to the circuit whenever Vout goes negative, because we're not connected to the power supply for negative going outputs, so C2 supplies the energy we need to go negative on the output. Okay, now let's take a look at it with no signal applied. Since there's no bias on the bases, Q1 and Q2 are both in cutoff, and ICQ equals 0. If the transistors are matched, then they'll divide the power supply evenly between them. VCC over 2 dropped across both transistors. Okay, these two capacitors, C1 and C2, will both charge up to half of the power supply as well. So the base node and emitter nodes will both be sitting at VCC over 2, so we have no bias on the transistors. They're in cutoff. Whenever Vin goes positive, this base node goes positive, which reverse biases Q2, sending it deeper into cutoff, while tending to forward bias Q1. Once we exceed 0.7 volts at this node, Q1 turns on and we get this output that is a replica of the input, but it's about 0.7 volts smaller in amplitude. Now for negative going inputs, Q1 goes into cutoff, Q2 goes into the active region, and it allows capacitor C2 to force current flow counterclockwise around this loop, giving us this negative going output, and it's about 0.7 volts shy of the most negative value of the input as well. All right, now this region where we're not getting any output is something that's called crossover distortion. All right, that's very bad for audio applications, okay? It may be all right if we're using this amplifier to drive, say, a motor or some kind of solenoid or something, but for audio applications, this is absolutely terrible, and we'd like to get rid of that. All right, we're going to find a way to do that shortly, but let's derive some equations for this circuit first, okay? So what we've got here is the two transistors operating. For positive going signals, Q1 is on, and for negative going signals, Q2 is on. All right, let's look at Q1 because we're mostly used to looking at NPN transistors. All right, the voltage gain of this amplifier is simply given by the voltage divider equation. We've seen it many times for the emitter follower. It's RL over RL plus R prime E, and it's usually approximately equal to 1. Now, you may be wondering, what's this R prime E? Well, it's the average emitter resistance over a wide range of currents. Remember, this is going to be a power amplifier, so Q1 is going to be completely off, and it's going to be driven heavily into conduction if we're driving a low resistance load. So little re, remember, was defined as V sub t over ICQ. For this circuit, ICQ is 0, so that gives us infinite little re, and that's not going to be workable for this circuit. So that's not a valid parameter here. We are using the average emitter resistance over a wide range of current. Now for a low power transistor like a 2N3904 or a 3906, typically R prime E is around 1 ohm, and that's what we're going to use as our approximation. If we're using a power transistor like a 2N3055 or a TIP41 or something similar, R prime E is about 0.1 ohms typically. Now also, we've been using a typical beta of 100 for these small transistors. Typical power transistors have a lower beta, so we're going to estimate power transistor beta as being 50. Okay? Now, let's take a look at the input resistance. Looking from the perspective of V in, we're just going to see R prime E plus RL times beta. All right, so we have that over here. Looking at the output resistance, okay, we set ourselves in place of RL and look back into the emitter. We see R prime E, and if there's no source resistance, that's it. The output resistance is approximately R prime E. If we happen to have a significant amount of source resistance in V in, then we're going to see that divided by beta plus R prime E. Okay, so these are our output resistance equations. Usually it's close to R prime E, but sometimes we'll have to go with this one. All right, now notice I've drawn C2 here in dashed form just to remind ourselves that on negative going outputs, C2 is the component that supplies energy to the load because Q1 is off and it isolates us from the power supply. All right, so C2 is a very important function in this amplifier. Okay, now this crossover distortion, this is not a good thing and we want to get rid of it, and the way we do that is by going to what's called Class AB biasing. All right, so in a nutshell, in Class AB biasing, we're just moving the Q point slightly into the active region. So it's not really Class A, and it's not Class B either, so we call it Class AB. The transistor is biased slightly on, just enough to get rid of the crossover distortion. The efficiency is still a maximum of about 78%. We're always going to be less than that. The conduction angle of the transistor is now pretty darn close to 180 degrees because we've gotten rid of the crossover. That's the whole idea here. The amplifier can have good linearity if it's well designed using a push-pull configuration. It's mainly used in power amplifiers, and we're normally going to bias up the transistors using something called a current mirror. Now that's something new we haven't talked about before. We're going to have to get into that next, but it's a really important circuit. We're going to use it a lot in other applications down the line, so this is a good point for us to talk about the current mirror. So let's do that now. Okay, here we've got a current mirror. All right, the idea here is that we've got a diode directly in parallel with the base emitter junction, and in order for this to work properly, we have to have matched characteristics for the diode and the transistor. That is, they have nearly identical transconductance curves. The idea is if we establish a current down through the left side of the circuit, I1, if the base current is small, and it will be in a normally well-designed circuit, the diode current is about the same as I1, and it's going to be given by VCC minus a barrier potential drop divided by R1. That is VCC minus VBE over R1. Now, the collector current will be almost identical to I1. That's why it's called a mirror. Okay, now why is that? Well, if we establish I1 through the diode and it produces this drop VBE across D1, it's also across the base emitter junction of the transistor. If they're identical, then by definition, they both have to be carrying the same current. And that's the whole idea behind the current mirror, matched transistors. Now, it can be kind of hard to match diodes to transistors if you're using discrete parts. It's not bad. In fact, it's very easy to do it using integrated circuit techniques, but for discrete parts, that's not easy. So what we might do instead of using a diode is get two matched transistors and connect one of them up as a diode. If we connect the base to the collector of a transistor, we have a diode, and that's very often done to facilitate matching between these two devices. All right, so let's take a look at a sample problem here, okay? So we've got a current mirror using a diode connected transistor, and we want to figure out what IC is, okay? So we'll find I1. That's going to be 9 volts minus 0.7 divided by R1. So 9 minus 0.7 is 8.3 volts. Divided by 8.3 k ohms is 1 milliamp. So I1 should be 1 milliamp. Whoops, let's turn on the pencil here. 1 milliamp. And IC should also be 1 milliamp. Okay? Now, I did a PSpice analysis of this just for the heck of it, and rather than bring it all up, I just copied and pasted the schematic here with the currents shown, and PSpice tells us I1 is 1.004 milliamps, good agreement, and IC is 1.086, close enough to 1 milliamp, and there we go. All right, now, you might be thinking, why are we using this instead of just one of the biasing circuits we've looked at before? And the main reason is, remember, this transistor Q2 in the circuit is part of the output of a power amplifier, and we don't want to stick an emitter resistor in here because that would cause a lot of power loss and it would reduce the voltage gain of the amplifier. So if at all possible, we prefer not to use emitter resistors in these power amplifiers. This circuit allows us to get away without doing that. Now you might be thinking, why not just put a resistor over here in place of the transistor? And we're going to take a look at that right here. Why use a current mirror? All right, why not just stick a variable resistor here and trim it till we get the collector current we want? Well, let's say we do that. We set ICQ to some value and the transistor warms up a little bit. Now what happens when a transistor warms up is its transconductance curve effectively shifts to the left a little bit. As temperature goes up, the transconductance curve shifts over this way. All right, so let's say we adjusted it at temperature of 20 degrees and it warmed up a little and our curve shifted over. Because it goes up exponentially and our bias current stayed the same, we're going to get a pretty good increase in collector current. Then what might happen is the transistor is going to get a little hotter yet because it's carrying more current. Its temperature goes up, so the curve moves over a little more, current goes up, and so on and so on, and we get what's called thermal runaway. This circuit is very susceptible to thermal runaway. That's why we can't use this approach, okay? Now, what happens with a current mirror is if we can keep D1 and Q1 at the same temperature, as temperature goes up, both of the curves shift by the same amount, and we cancel out the temperature sensitivity. So this circuit is much more stable with temperature than this arrangement. That's why we use the current mirror to begin with. Okay, it's less temperature sensitive than a lot of other biasing arrangements, and we don't want to use an emitter resistor here. So there you go. All right, so let's take this current mirror idea and apply it to our amplifier. All right, so here we've got class AB biasing. We've added a current mirror to Q1 and a similar current mirror to Q2, and we're coupling our signal into the junction between the two diodes. All right, we set up ICQ equal to I1 by using this equation. We've got VCC, 2 barrier potential drops, and the 2 resistors. So it's VCC minus 2 VBE divided by R1 plus R2. Now that's all well and good if the transistors and diodes are matched, but if they're not, which is likely to happen if you're building this at home, then generally what you can do is pick R1 and R2 that are relatively large, maybe even up to 10K or more, just to ensure that ICQ is a couple of milliamps. We don't want a lot of current here, but the absolute value of this current is not important, as long as it's enough to eliminate the crossover distortion and not cause too much power dissipation at the Q point. All right, if we're using small transistors, if it's just a low power amplifier, and we're using 2N3904s or 3906s, then we could use 1N914s or 1N4148s for D1 and D2. If we're using power transistors like 2N3055s, typically these are going to be bigger diodes like 1N4001s or something like that, or even transistors hooked up as diodes. All right, let's see. Next, let's develop all of the equations for this circuit, and we're going to look at it just for the positive half cycle where Q1 is turned on and Q2 is in cutoff. All right, now looking at the amplifier, from the voltage gain perspective, nothing has changed. AV is still equal to RL divided by RL plus R prime E. All right, let's look at the input resistance. Now our source is looking at the biasing resistors. I'm ignoring the diodes for right now, but we're going to see R2 in parallel with R1 going to ground through VCC. Now, there's a little bit of ambiguity here, let's call it, because R2 is not going to appear in the circuit for all of the input, but part of it, okay? So I'm just going to include both of the resistors in this calculation, okay? Because it's a little bit on the conservative side. All right, so what we're going to see is R2 in parallel with R1 in parallel with beta times R prime E plus RL. Okay, in other words, Rin is equal to R1 in parallel with R2 in parallel with beta times little r prime E plus RL. Okay. Now, the output resistance, if we have no significant source resistance, is simply going to be R prime E again, because the source grounds this node. Okay, so R out can be approximately equal to R prime E, a pretty low value. If there's a significant source resistance, then we're going to see R out equal to RS in parallel with R1 in parallel with R2 divided by beta plus little r prime E. Okay, we're going to have to account for this base stuff. All right, so those are our small signal characteristics for this amplifier. All right, let's figure out the large signal characteristics. That is the maximum current that we're going to get and the maximum power out. All right, let's start by calculating IC sat. All right, IC sat is approximately equal to VCC over 2 divided by RL. And when we divide by RL, it's the same thing as multiplying by 1 over RL, so it's VCC over 2 RL. All All right, that's the maximum current, and that's kind of assuming the transistor has a VCE sat of 0. All right, normally a pretty accurate approximation. All right, VO max is simply approximately VCC over 2. If the transistor saturates, we're just going to get this supply voltage, VCC over 2. And remember, I'm using VCC over 2 because we've got C2 charged to half of the power supply voltage down here, and with VCC up here and VCC over 2 down here, it just works out easier to represent it this way. All right, now power out max, PO max, is equal to either I squared R, so that's going to be IC sat squared times RL, or we could use VO max squared divided by RL, so that would be VCC squared over 2 squared times RL, so 4 RL. These are both equivalent ways to find the maximum power out. And of course, power out RMS is equal to PO max divided by 2. All right, now what about the transistors in the amplifier? How much power are they going to be dissipating? Well, here's what I'm going to do. I'm going to assume the amplifier runs at 50% efficiency. Remember, the maximum theoretical efficiency is, what, 78%? We're going to be less than that, and 50% is a pretty good estimate of what the average efficiency is going to be. So if we assume eta equals 50%. Okay, now that's not a very nice eta. That means if we're, say, delivering power out to the load of 10 watts, then the amplifier itself is dissipating 10 watts. That's 50% efficiency. 10 watts to the load, 10 watts from the amplifier. But remember, the work the amplifier is doing is split between two transistors, Q1 and Q2. It's not shown here. So each transistor is doing half of the work. So PD for Q1, let's just call it PQ1, is equal to 5 watts. And power for Q2 is also equal to 5 watts. They total up to 10 watts because we've got 50% efficiency. All right, so let me get rid of my messy writing here and bring over these equations so that you have something, nice to work with. All right, I'm a nice guy. I like to do this for you guys. Okay, so here we are. Let's drag this back over, and here are our small signal analysis equations for the voltage gain, input resistance, and output resistance, and the large signal analysis equations, IC sat, VO max, PO max in all of its forms, and the power out to the load, RMS, and the heat or power dissipation of the two output transistors, assuming eta equals 50%. Okay, so there you go. Let's put this together into a actual amplifier circuit. All right, so here we've got two power transistors. Tip 41 is the NPN, and a tip 42. These are complementary transistors. They're power transistors, so right off the bat, I'm going to estimate their R prime E as 0.1 ohms. All right, so let's find IC1, ICQ, and I1. Okay, we've got 15 volts, and let's pull up our calculator here. So we've got, we could do it this way. We'll do 7.5 minus 0.7 divided by 4700 is about 1.4 milliamps. So we've got about 1.4 milliamps flowing down through these resistors. That means we should have about 1.4 milliamps of collector current. That should be enough to slightly turn these transistors on and eliminate crossover distortion and not waste too much power while we're sitting here just idling. And by the way, sometimes ICQ is called the idling current for an amplifier like this. All right, what's our voltage gain? All right, AV equals RL divided by RL plus R prime E. So we've got 10 ohms divided by 10.1. Well, that's pretty darn close to 1. So let's just call our voltage gain 1. The input resistance, okay, that's a little more complicated. Rn is approximately R1 in parallel with R2 in parallel with beta times little r prime E plus RL. Okay, so we've got 4.7. Let's deal with this beta times little re first. R prime E is 0.1 and RL is 10. So let's just estimate this as 10, okay? And beta is 50 for this kind of transistor. So 50 times 10 is 500 ohms. So we've got 500 in parallel with 4700 in parallel with 4700. Whoops, still close enough. Equals about 412 ohms. Okay, so Rn is around 412 ohms. We could just call it 400 ohms, okay? That's close enough. We're approximating things. This is about 412, but we're saying it's close to 400. Okay, the output resistance. Well, since our source has no internal resistance, when we look back through the transistors, all we're going to see is R prime E. So that's our approximate output resistance, R prime E, which is about 0.1 ohms typically for a power transistor. All right, the current gain. Remember, A sub I is equal to AV times Rn over RL. Our voltage gain is about 1. Rn is about 400 ohms. And our RL is 10 ohms. So that's 400 divided by 10 is 40 times 1. We've got a current gain of about 40. Okay? Remember, current gain always has to be less than beta, and we're using beta equals 50. So that's a good sanity check. All right, our power gain, A sub P, is equal to AV times AI. Hopefully you remember that. So we've got AV of 1 times AI of 40. So it's also approximately 40. So we've got a power gain here of about 40. Now what's IC sat? Well, remember IC sat is approximately equal to VCC over 2 RL. Okay, so 15 volts divided by 20. Let's see what we've got here. 15 divided by 20 is about 750 milliamps. Okay, so IC sat is 750 milliamps. All right, VO max is approximately 1/2 of VCC, so that's 7.5 volts. And our maximum output power, PO max, is IC sat squared times RL. Let's use that version. Okay, so we've got IC sat is 0.75. Okay, squared times 10 is let's just call it 5.6 watts. Okay, it's not going to be quite that, but close. 5.6 watts. And our power RMS is simply half of that, so we divide by 2, and we get about 2.8 watts RMS. Okay, 2.8 watts RMS. That's not too bad. We're only working with a 15-volt power supply, so yeah, it looks pretty reasonable. Okay, so if you built this amplifier and you had a 15-volt supply, you could get pretty decent sound out of this thing. All right, now what I want to do next is look at this circuit with a bipolar power supply. Okay, but before we do that, let's take a look at our transistors here for a second. Okay, the tip 41 and tip 42. All right, I put some of their data here just to get an idea what we're dealing with. All right, the tip 41 and 42 come in a TO220 package. They're very easy, cheap, relatively easy to get, and they're designed for general purpose amplifier and switching applications. We can get them in different breakdown voltages, VCEO. That means voltage from collector to emitter with the base open. Anywhere from 40 volts to 100 volts. The 40 volt version would work just fine in our amplifier. All right, maximum collector current is 10 amps peak, 6 amps continuous, so we're nowhere near the maximums for this transistor. All right, the DC current gain H sub capital FE, that's the DC beta, has a minimum value of 30, okay? And that's with 0.3 amps in the collector, okay? If we increase the collector current to 3 amps, our minimum beta could be 15, maximum is about 75, okay? So 50 is a good estimate. Now the small signal current gain, that's H sub lowercase fe, that's the same thing as beta AC, has a minimum value of 20. They're not giving a maximum, so again 50 is probably a good estimate. And if you happen to be using 2N3055s or the complement MJ2955s, some of their parameters are gain anywhere from 20 to 70, that is beta. Let's see, our maximum collector to emitter voltage is 60 volts, and these can carry a collector current of up to 15 amps, and the power dissipation can be as high as 115 watts. Now there are some caveats to this stuff, and this video is already long enough that I'm not going to talk about heat and heat sinks and power dissipation and stuff like that. We'll save that for another day. But I can assure you there's a lot to it, and we'll come back to this sometime. But for right now, there's a quick run through of some transistor specs. Okay, now back to this amplifier. As I said before, I'm going to operate this thing from a bipolar power supply now. And one of the advantages of that is that we can get rid of our coupling capacitors, okay? We don't need C2 to supply energy on the negative going outputs because we have a negative power supply to do that, so we don't need a cap here. And if Q1 and Q2 are matched, they should both be dropping equal voltages, and the base node and emitter nodes should both be sitting at 0 volts DC. Okay, so we're not going to have any DC current flow through our source or our load because in equilibrium we're sitting at 0 volts here. All right, now all the equations that applied previously apply to this one with some slight modifications. Okay, ICQ is VCC plus VEE minus 2 barrier potentials divided by R1 plus R2. That should make sense, okay? That's a pretty straightforward modification. IC sat, well, if Q1 is turned on, it's VCC over RL. If Q2 is turned on, it's minus VEE divided by RL, but their magnitudes are the same, so we just go with this equation. VO max is VCC or minus VEE, so I could have plus or minus here, but again, these are equal magnitude supplies, so let's just go with the positive values. PO max IC squared times RL, just the same as before, except our IC sat is going to be a little different. PO max is V squared over RL. RMS, PO max over 2. And assuming efficiency is 50%, Q1 and Q2 both dissipate the maximum output power RMS divided by 2 because the work is split between 2 transistors. Okay, so nothing too surprising there. I think it all should make sense. And I know this has been a long slog through this video. Hopefully you're hanging with me. Okay, this is going to be very useful to us in the future. So I hope you're hanging in there, and I'm sorry the video is so long, but it's almost over, okay? Because the next thing I'm going to do is give you a problem to work on, okay? So we've got a bipolar power supply, and this time we're driving an 8 ohm loudspeaker, and I just want you to figure out all the usual stuff. How much power are we going to deliver to this speaker, and how much power do these transistors dissipate when we're delivering maximum power to the load? Okay, so hopefully this was somewhat interesting. It was a long, hard video for me. I'm really tired of talking, so I will see you guys next time around.